You see it absolutely everywhere. That simple gray powder that, well, builds our entire world. But what if I told you that cement isn't just some simple mix? Oh no, it's actually the result of this incredible chemical transformation, a story that's written at a scale so small you can't even see it. So let's dive in and find out what's really going on inside.
And this, right here, is the big question for today. We're going to move way beyond just a simple list of ingredients. We're going to uncover this hidden, complex architecture of crystals that gives concrete its unbelievable strength.
Okay, so let's start with the basics. Like any great recipe, cement starts with just a few key ingredients. In this case, there are 4 main oxides that make up pretty much everything that goes into that fiery kiln.
Now, to keep from writing out these long, clunky chemical formulas all the time, cement chemists came up with a really simple shorthand. So, calcium oxide is just C, silicon dioxide becomes S, aluminum oxide is A, and iron oxide is F. Think of it like an insider's code that makes talking about these super complex reactions way, way easier.
This is really where the magic happens. These raw materials, they get heated up to ridiculously high temperatures inside a cement kiln. And they don't just, blend together like you're mixing a cake batter. No, they chemically react and completely rearrange themselves into brand new compounds. They become something totally different.
So the big question is, how in the world do you figure out what those new compounds are? Well, for a long, long time, the best tool anyone had was basically a prediction. Back in the early 20th century, a scientist named R.H. Bogue developed a set of equations to try and estimate the final composition, all based on what you put in at the start.
Bogue's method gives us what we call the potential composition. And that word, potential, is doing a lot of work here. It's so important because it's not a direct measurement of what's actually in there. It's more of a highly educated guess, a theoretical outcome based on that starting recipe.
The logic behind Bogue's equations is really a step-by-step process. First, it just assumes all the iron goes to form one compound, C4AF. Okay. Then it uses whatever aluminum is left over to calculate the next compound, C3A. And it just keeps going down the line like this until all the starting ingredients are accounted for in these new, predicted compounds.
But here's the thing. Even the scientists admit this is just an estimate. As this quote tells us, it's a way to get a potential formula. It's a really useful starting point for sure, but it kind of hints that the real story is a bit more complicated. Because let's be honest, the real world rarely behaves as perfectly as a clean set of equations.
And that brings us right to the heart of the problem. Bogue's calculations were absolutely brilliant for their time, but they have to rely on some, let's call them ideal assumptions that just don't hold up in the fiery, chaotic, messy reality of an actual cement kiln.
And this right here shows you the disconnect perfectly. Bogue's math assumed the chemical reactions had all the time in the world to reach a perfect, stable balance. But in reality, that material is in the hottest part of the kiln for maybe 30 minutes. It's fast, it's furious, it's messy. He also assumed only 4 simple compounds would form, but we now know that much more complex things can happen, like solid solutions, where atoms of one thing can kind of sneak in and substitute for another inside a crystal.
So this is the big question, right? If the old school math just gives us a really good guess, what kind of technology lets us see the actual final product? How can we, look under the hood and see what's really there?
And that leads us right into modern science, because today we have these incredibly powerful techniques that go way beyond just prediction. They let us directly measure the final structure of the cement clinker. Those are the little stony pebbles that come out of the kiln.
The 2 main tools we use ask 2 totally different questions. Think of it this way. X-ray fluorescence, or XRF, is like reading the ingredients list on a box of cake mix. It just tells you what's in there. But X-ray diffraction, or XRD, is like looking at the finished baked cake. It tells you how all those ingredients were cooked and arranged into their final, beautiful crystalline forms.
And this was a fundamental shift in how we understand cement. It's a total game changer. Because of tools like XRD, we now know that cement isn't just a physical blend of powders. It is a highly structured material, an intricate, microscopic landscape of interlocking crystals that were all forged in the heat of that kiln.
So let's meet the main players in this tiny little world. First up, you've got alite. These are the large, irregular workhorses that give concrete most of its early strength. Then you have belite, which are smaller, more rounded, and they contribute to strength over the long haul. And then, filling in all the gaps between them, you have the ground mass, which is a fine mix of all the other stuff.
So why does any of this microscopic detail actually matter? Well, it matters because this invisible architecture is directly responsible for how the concrete we build our cities with actually performs. This is why that jump from prediction to direct observation was so incredibly revolutionary.
So when we actually measure the final composition, this is typically what we find. Alite, that's C3S, makes up about half of the cement. Belite, or C2S, is another quarter. And the rest is made up of those other phases, plus a little bit of gypsum that gets added at the very end of the process.
I mean, just think about that for a second. Put them together and just two main types of crystals, alite and belite, make up roughly 80% of the entire cement clinker. They are, without a doubt, the absolute backbone of concrete strength.
And that's really the ultimate takeaway here. Everything from how quickly a sidewalk hardens to the final crushing strength of a skyscraper, it's all determined by the specific size, the shape, and the amount of these tiny little crystals. The microscopic world literally dictates our macroscopic reality.
So the next time you're walking on a pavement or you look up at a building, I hope you won't just see gray stone. Maybe now you'll see that hidden, complex landscape of crystals, all working together. What kind of invisible structures are you going to imagine now? Thanks for tuning in.